All right, if because of the way because I was trying to do I'm doing a screen recording on QuickTime here, and then tried to show you a movie on the screen, and that just doesn't work very often, but very well. So you can go to I've put the Shalane Flanagan video on for you to watch. And there are a lot of very interesting and cool videos that I've loaded because there's friction and drag, and we're also going to talk about air pressure. We're combining a lot of stuff here. So friction in the comic, talk about Sir Mix-a-Lot. We're going to get our friction on today, and so here we go. When an object moves or attempts to move across, there's a force that is parallel to the surface. This is called the frictional force. There are two types of friction. There's static friction, and then there's when two solid objects are stationary, and then there's kinetic friction. Okay, when one against the other, the shoe and the ground are not in relative; they don't slide. Okay, therefore this is static friction. In fact, static friction is what pushes you forward when you walk. All right, when your foot hits here, you push back on the earth. Newton's third law, the earth goes, nice try, buddy. I'm going to push back with you the same force, and you're going to go forward because I am so massive, I'm not moving, but you are. All right? So that's how that works. That's the way we walk. If you've got ice down here and no friction, whoosh, 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 you're not going anywhere. Okay? All right. Kinetic between two sliding frictions when you slide things. Okay. A classic example, of course, is a sled. And we're going to look at some great sled dogs too in this. All right. The wheels are spinning and the drag racer is going to the left. Which way is the friction from the ground on the tires pointing? All right. So he's burning. Okay. So he's going. The wheels are spinning and the drag. So the wheels are going this way and he's going this way. So it seems like the wheels are pushing this way, and they are. But the Earth's still so much more massive than that dragster, pushing it forward. Okay, the wheels are pushing them forward. As a matter of fact, when the wheels are spinning, the drag racer to the left. Which way is the friction force pointing? Boom, forward. Just like when we're walking, drifting, and all that. Now, here's something I want you to know. Okay, from our notes, because I won't be able to get into. I don't know if I'll be able to today to get into our good old onto Blackboard so you can see what's going on. So I can go through the questions with you, but we can do this. All right. So this is exercise 9. Excuse me, I am catching a bad cold. I think we all are as the weather's getting cooler, and I like having the cooler weather. I hope we have a fall, and I hope we have a winter too. I miss those, those cold, snowy days. All right, but that might be, as we say, the new normal, and I hate that phrase, new normal, because you know what that means? That means we're tolerating it, and we're not doing anything about it. All right, so pisses me off. All right. Anyway, here we go. All right, so here's what we've got. We've got they burn off wheels because it gives them more surface area to push on. All right, it increases burning the wheels increases the static friction. It's like putting spikes. It increases the static friction. Okay, on a dragster. All right, so that's one of your questions. So, and I don't know if we get down to where we answer that or not. All right, so we got a lot of stuff to go through here. Okay, you can see the drifting video. All right, kinetic friction. Kinetic friction is a force that a rigid surface exerts on a sliding surface of an object with which it is in contact. This is parallel. That is parallel to the surface. Okay. UK, that little UK here, is known as the coefficient of kinetic friction. All right, so right away, let's go into how do we calculate frictional force? All right, static frictional force. Let's do static. Here's a static frictional force, and this is what it looks like. All right, got a block, good old block. It's got a weight going down, and the ground's going, pushing back up, what we call the normal force. Okay, so we got mg, weight going down, normal force going up, so the sum of these forces are equal to 0. All right, the static frictional force, mu sub s is equal to the normal force times, the static frictional force is equal to mu sub s times the normal force. And different substances have different coefficients. Here is mu. What I'm saying is mu, as in the Greek mu, sub s. That is what I'm saying. Okay. And that means that's the static frictional force. And this is the coefficient of static friction. All right? That's when things aren't moving. All right? And Fn, as long as we keep things flat, and we're always going to do it flat for this course, Fn is equal to mg. Because the sum of the forces in the y direction equals 0, so therefore I've got Fn going up minus mg coming down. I set those two, and I add mg to both sides. I get mg equals the normal force. All right? So Fn equals mg. So example. Let's say the static frictional force for snow, or the coefficient of static friction for snow, is 0.16. And it's just a number. It doesn't have units. All right? Let's say human is 45 kilograms. There's a mass of 45 kilograms standing on the snow. All right? So here we are. Standing on the snow. Here's a human. Here's me or Barack Obama, whichever one you prefer, standing on the snow. All right? And the coefficient of friction, and they're 45 kilograms. Now, I want to know, what is the minimum force if I've got a rope tied around me and somebody's pulling it like this, and I've got like little, like skates on or something like that, and I'm on a pond. What is the minimum force that's going to get me to move? Okay? What is the minimum force? All right? And so that force to get me to move is going to equal mu of s times mg. That's the minimum force that's going to get me to move. So this would be 0.16 times 45 times 9.8. That's going to be the minimum force that's just going to get me to move. Okay, and that comes out to be 70.56 newtons. Okay? That's the minimum force that's going to get me to move. All right? But then once I move, once I break that, then the kinetic frictional force is usually less, is always less. The kinetic frictional force, mu of k, is always less than mu of s. So let's say for snow, it's mu of k is equal to 0.11. So now, if you keep applying that, let's say we keep applying that same force of 70.56 newtons on me. So here I am. Whoops. And I think this might be one of those cases where where I'm getting carried away. All right, so now we're still applying the 70.56 Newton force. I've broken free. Boom. Instantly. In other words, you pull, and then bang. Then you start going. All right? All right, so you pull hard until you get to that max force. So you get to that minimum or the maximum force that you need to get you to move. All right, which is this is this. All right, got us to move. Now we're moving. All right, so now we've got some of the forces in the x direction is equal to my mass. Remember we said the mass is 45 kilograms times the acceleration. So now I've got an acceleration. All right, because I've got this force pushing me, but there's this kinetic frictional force opposing me. I forgot to draw that over here. I've got this force going this way and a static frictional force going this way. And so the sum of the forces in the x direction are equal to 0, which is equal to F minus F of S. And so the F of S equals that force that's going to get me to move. Okay? But now, that force max minus F of K, that's a smaller force. So I'm actually going to accelerate now. I'm going to get going faster. And so I've got 45 times A, I don't know what my acceleration is equal to 70.56 minus 0.11 times 45 times 9.8 times mg, because F of K is equal to mu of K times mg. All right, so I got 70.56 minus 0.11 times 45 times 9.8, bang, 22.5. That's all that, and I wind up with 22.5 newtons equals 45 times A. And so that my acceleration then is 22.05 divided by 45 kilograms. And that gives me, this is quite a lesson, wasn't it? 0.49 meters per second squared. Hey, you guys just went to physics 240 there for a minute. Sorry. So I'm going to stop here before I go crazy.